let us continue our discussion on properties of regular sets. In particular, we were discussing this example, and with respect to this we have defined a relation. The relation says a string x and y belonging to sigma star. One can relate using this relation x related to y if and only if, starting from q naught, look at the state at which the automaton will be on completing x, similarly on completing y. If they are same, then these two strings are related. It's a string, so let me use delta cap. So this tells you that any two strings in sigma star can be related using this. Subsequently, we have proved this relation as an equivalence relation, which means this relation partitions the underlying set, which is sigma star, into equivalence classes. Correct? This is all we have seen. And most importantly, it partitions this into finite number of equivalence classes, one for each state. What am I saying? You get to see sigma star is partitioned into E1 union E2. What is E1? E1 is all those x such that delta cap of Q0 comma x is Q0. The output state is Q0. E2 is all those x such that delta cap of Q0 comma x is Q1. Because when you simulate x with respect to Q0, it can either end in Q0 or it can end in Q1. And for this example, one can also describe that if it ends in Q0, it can read any number of b's, or maybe reading b followed by a couple of a's, then it can come back to Q0 using this b, which means it is all those strings ending with b. Correct? And suppose the output state is Q1, which means you read a A or you read couple of more A's, then read B, couple of more B's, again read A, which means all those strings ending with A is precisely part of this. And with respect to Q0, even epsilon will be there. So now this tells you sigma star, every element is present in E1 or E2, and there is no element which is present in both, which means it's clearly a partition. Correct? That's one part. The other interesting part is the following. Because Q1 is our final state, the equivalence class 2 represents the set of strings accepted by the automaton, accepted by DFA. Correct? Which means we know that L is a subset of sigma star. For this example, L is precisely E2. And E1 gives you set of strings rejected by the automaton, or in case you want to get the complement, we can use E1. But for this automaton, the language is precisely this. So what is this telling us? Given a finite automaton, through this equivalence relation, you get finite number of equivalence classes. And one of them, in general at least one, One of them is representing the language, set of strings accepted by the automata. In general, this is the larger picture, because when we do this relation delta cap of q0 comma x, the output state can be q0, or output state can be q1, output state can be q2, so on up to output state can be qn minus 1. Let's assume there are n states in the automata, correct? And there will be an equivalence class corresponding to q0, which means all those strings such that q0 comma x is q0. There will be an equivalence class corresponding to q1, and so on up to there will be an equivalence class corresponding to qn minus 1, correct? Then identify the final states in the automata if, say, q2 and q4 and say qn minus 1 belonging to final states. Then what is the language? Then the language accepted by the automaton is the equivalence class corresponding to q2 union equivalence class corresponding to q4 union equivalence class corresponding to qn minus 1, correct? So look at the equivalence classes corresponding to the each state in F, or basically the final states, take their union. That's precisely our language. So it is sigma star finite automaton through transition states. It is looking at sigma star like strings accepted by the automaton, strings rejected by the automaton, and all those states which are not present in F, they will correspond to strings rejected by the automaton. They will help in answering the complementary question. So through finite automaton states transitions, one can look at sigma star as a partition of two sets, one strings accepted by the automaton, strings rejected by the automaton. The same picture one can also get through this equivalence relation. Keeping this as inverse of discourse, you can partition them into finite number of equivalence classes with respect to this relation, and you get to see that language is precisely union of some of the equivalence classes. Fine. The other interesting part is the following. This relation, this is on one side. This relation is also right invariant. So x related to y implies xz related to yz for all z belonging to sigma star. So what it says is if x and y are related, which means delta of q0 comma x equals delta of q0 comma y. Now you concatenate z, which means delta of q0 comma x z is same as delta of q0 comma y z. So it says if x is related to y, then one can also infer x z related to y z. Okay. So you say a relation is right invariant if this property is true. Relation is right invariant if and only if for all z belonging to sigma star, x related to y implies xz related to yz. In a relation, if two pairs are related, then if you can infer for all z xz related to yz, then you conclude the relation is right invariant. What it says is if the output states are same with respect to x and y, then the output states will be same with respect to xz and yz. Now we will show that this relation is indeed right invariant. Okay. So to show that it is right invariant, we make use of this. So consider delta cap of q naught comma xz. So what are we supposed to show? We need to show this, but to show this we will show that delta cap of q naught comma z equals delta cap of this, delta cap of q naught comma yz. So this can be rewritten as delta cap of q naught comma x comma z, and now for this we operate one more delta cap. Note that by definition x is related to y, which means we know that this is precisely delta cap of q naught comma y comma z, because premise says x is related to y. If x is related to y, by definition delta cap of q naught comma x is same as q naught comma y, which means this is delta cap of q naught comma yz. So what is that we have shown? So conclusion, delta cap of q naught comma xz is same as delta cap of q naught comma yz. So with this you can conclude xz is related to yz, and this is precisely what we want. So this clearly tells you our relation R is right invariant. Okay. So you get to see that if x is related to y, then xz is related to yz. So to show that xz is related to yz, we will show that delta cap of q naught comma xz is same as delta cap of q naught comma yz. The output state at which the automaton will be when we operate xz with respect to q naught will be same as the output state at which the automaton will be when we operate yz on q naught. This can be rewritten as q naught comma x comma z, and by definition x is related to y, or given the fact that x is related to y, so we rewrite this one as q naught comma y, because when x is related to y, by definition you get to see q naught comma x is q naught comma y, then which can be rewritten as q naught comma yz. Therefore we conclude the xz is related to yz, which means R is right invariant. So what we have shown now is this relation, in addition to satisfying equivalence property, it is also satisfying the right invariant property. Okay. So what is that we have shown? That we have a relation R which says x related to y if and only if delta of q naught comma x is same as delta cap of q naught comma y. We know that this relation is an equivalence relation, and we also know that this relation is right invariant, and we also know that the language accepted by the automaton is union of some of the equivalence classes, and EI corresponds to a final state. Okay, it is an equivalence class corresponding to some final state. Correct? So now, what is interesting is the following. So L is regular, or you find a DFA if and only if there exists a right invariant equivalence relation such that L is the union of equivalence classes corresponding to final states of M. M is the deterministic finite automaton. So we get to see that if L is regular, then there exists a right invariant equivalence relation such that L is the union of equivalence classes corresponding to final states of M. If you look at this right invariant equivalence relation, it is not an arbitrary one, it is having finite index. What do you mean by finite index? Number of equivalence classes is finite. So what we have is a right invariant equivalence relation such that L is the union of equivalence classes corresponding to final states of M. And interestingly, if you are given this, you can also construct an automaton out of it, which is why it is if and only if. And this is a famous result in automata theory. This theorem is due to Myhill, Nerode, and it is known as Myhill-Nerode theorem. So what we have seen is through this equivalence relation one can understand sigma star, or through constructing a finite automaton one can understand sigma star, and they both are one and the same through this proof or through this statement. Now the interesting part is the following, because it's if and only if. What it says is the regularity can be checked via this. To show that something is regular, you come up with a right invariant equivalence relation having finite index such that L is the union of some of the equivalence classes, meaning equivalence classes corresponding to final states. And in the forward direction, L is the union of equivalence classes corresponding to final states. But when you try constructing the automaton, you see that language is corresponding to union of some of the equivalence classes. When we say sum of the equivalence classes, it is equivalence classes corresponding to the final states. Because of if and only if, we also get to see that L is not regular if and only if there does not exist a right invariant equivalence relation having finite index satisfying this property. Correct? Which means what is this telling us? Every right invariant equivalence relation, if you look at any right invariant equivalence relation, every right invariant equivalence relation is having infinite index. So number of equivalence classes will be infinite in nature. So you get to see that if the underlying language is not regular, then there does not exist an equivalence relation having finite index, or rather every right invariant equivalence relation we come up with will certainly have infinite number of equivalence classes. If we show that for so and so language like a power n, b power n, any right invariant equivalence relation will certainly have infinite number of equivalence classes. With that we can conclude it is not regular. So this way of looking at the set sigma star is trying to understand regularity, and through that process we are able to come up with one more way of showing that certain languages are not regular. Either we can use pumping lemma or we can use Myhill-Nerode theorem to show that certain languages are not regular. Okay, it's an interesting way of looking at sigma star from two different perspectives, and there are beautiful applications as well.